Hello everyone. So I'm Florian, and today we'll talk about research on the use of locality-sensitive hashing systems for privacy. This is a joint work with Karel Kubicek, Carlos Cutroni, and David Bazin from UTH Zurich. So to begin, let's briefly define locality-sensitive hashing. LSH is a technique that maps similar objects to the same hash with high probability. Comparing the hashes instead of the objects allows for more efficient procedures. Some of the applications LSH has been used for are plagiarism detection, duplicate website detections, dimensionality reduction, clustering, and computer security. And recently we saw application in privacy. So Apple has recently proposed using LSH to ensure privacy and usability of collected data. Apple aims to detect child sexual abuse material in iCloud photos while preserving user privacy. It uses LSH to detect the presence of content similar to abusive images on a device without learning anything not related to the abusive images. The EU is also proposing similar approach to combating CSAM. Google FLoC is a system for private targeted advertising. It uses Cmash, a popular LSH function, to cluster together users with similar browsing history. The MinHash hierarchy system uses MinHash, another popular LSH function, to analyze traffic trajectories. Those proposal assumes that the hashes from private input can be made public. However, LSH hashes leak information about the inputs. Since the hashes do not provide security properties like pre-match resistance, the privacy implication of this leakage did not seem to be a serious concern for those proposals. However, it gives room for attacks. We will focus on the last two systems, starting with FLoC. One goal of FLoC is to provide key anonymity. That means that users should be tracked in group of at least k users. Another goal is to ensure privacy of the inputs to the LSH functions, namely the user browsing history. We present three kinds of critical attacks on FLoC. First, the pre-image attack on Cmash, using integer programming. Second, using the pre-image attack, we mount a Sybil attack that generates dozens of history per second, matching the target hash. We show this breaks FLoC's key anonymity and allows identification of individuals in a cohort. Finally, we use generative adversarial networks to partially reconstruct plausible histories from just the target hash. We start with the pre-image attack on Cmash. Let's briefly explain how Cmash is computed in FLoC with a simple example. The Cmash computation takes the domain names present in a user browsing history. For each of them, a fingerprint vector is drawn from a standard Gaussian. Fixed parameters are used as seed to make the sampling deterministic. We sum the entries in the same column, and to get the Cmash, we just apply a sign function element-wise to the sum vector. The sign for negative number is defined as 0. We repeat the same process with a slightly different history. The Facebook domain was replaced by Netflix. This produces a Cmash with only a single bit difference, and we see with this example that Cmash is a locality-sensitive hash. A slight change in its input only modifies some bit of the output hash. Integer programming is an optimization technique which allows us to compute a pre-image of a target Cmash efficiently. The inputs are the target hash on a set of websites. For each domain in the history, we can pre-compute its fingerprint vector represented by each column in the matrix. It is the same matrix as in the previous slide, but transposed. Integer programming then finds the vector x of booleans that determines if the website should be used or not. Multiplying the first row with the x vector, we obtain the inequality constraint necessary to match the first bit of the target Cmash. If the integer program returns a value greater than 0, we find a collision. And FLoC uses the Cmash to cluster similar users together. Therefore, using our pre-image attack, we can create fake browsing history matching the target Cmash and mount a Sybil attack on FLoC. A Sybil attack involves the creation of multiple fake entities to gain a large influence on a system. In the case of FLoC, we will flood the cohort with our own generated users. When we have a large enough number of users sharing similar Cmash prefixes, it becomes possible to isolate real users, breaking the key anonymity property. By generating a lot of users with the same Cmash, we can also force the central server to use longer Cmash prefixes. This results in users in a cohort sharing more similar browsing patterns. If we are interested in one of those green users, which will represent a real user, we can generate a lot of red users in the same cohort, and we'll be able to isolate the target real users. If we take the cohort 0, by generating 2 users mapped to that cohort, we force the central server to create one more cohort, and in cohort 0-1, we broke free anonymity as only one real user remains. Until now, we did not have a way to generate plausible user history for our attack. Generative adversarial networks are known for being able to generate new samples from the same distribution as the training data. And a GAN consists of a generator and discriminator that competes against each other to generate realistic synthetic data. Studies demonstrated that GANs can generate highly realistic faces, hard to distinguish from real ones. As confirmed by a user survey comparing real and synthetic faces, the first 2 rows shows the most accurately classified real and synthetic faces, and the last 2 rows shows the least accurately classified real and synthetic faces. Coming back to FLoC, for privacy reasons, we used users' movie history, and this was also used by Google for the evaluation of FLoC. The generator networks outputs a plausible user history X. The output x can be used by the integer program to find a preimage y matching a target C-match h. We can optionally apply the discriminator on the preimage y to get a score of how realistic the generated history is. The addition of the GANs allows to retrieve part of the browsing history for user in a target cohort. This breaks FLoC's claim privacy of user browsing history. In this histogram, we show the distribution of the common movie counts between two generators and our target real users' histories. From the histogram, we clearly see that the random movie generation has very little common movie with the target histories. On the other side, our GAN IP attack has a lot more movies with a high number of common movies. If we look at the tail of the distribution, GAN has 11 histories sharing 7 movies with the target, 3 sharing 8, and 1 sharing 9 movies. With this attack, we reconstructed on average 10% or more of the browsing histories for 30% of the users. This histogram shows us that the preimage attack combined with the GAN allow reverse engineering the browsing history from the user CMash, and those results compromise the privacy properties of FLoC. Here we see an example summarizing our attacks. At a given timestamp, we have cohort 1.1 with 3 users. Using our GAN IP attack, we can generate plausible user history matching cohort 1.1. Then after FLoC's clustering algorithm is run again the following week, the cohorts are updated, and cohort 1.1 is split in 2, and we can infer part of the website likely visited by real users in cohort 1.1.0. Now we'll analyze the MinHash hierarchy system. The MinHash hierarchy systems aim to compute statistics about vehicle trajectories while preserving the privacy of the trajectory behavior of users. One example statistic is to compute the most popular route in a city. The MinHash hierarchy system also claims to provide differential privacy for the vehicles. We refute that claim by providing a counterexample, but for time reason, we do not present it. We also provide a way to recover part of user trajectories, breaking the privacy of the trajectories. Similar to CMash, MinHash is an LHH function that works on sets. In the case of MinHash hierarchy, sets of vehicles that pass a given checkpoint. For a simple example, we define a MinHash function h composed of 2 hash functions, h1 and h2. We want to compute the MinHash for the set of value 1, 2. To compute the MinHash for the given set, we take the minimum value for h1 and h2, and we get the sequence 1, 0. Let's look at how MinHash is used in the MinHash hierarchy system on a simple example. On the left, we have a 3x3 grid of checkpoints going from A to I. The trajectory of 3 vehicles have been recorded. Each checkpoint will maintain a MinHash signature of the vehicle that passed by. We assume it only uses one hash function, the identity function. We keep only the minimum hash for all vehicles that visited. If we take checkpoint A, only vehicle 1 and 3 pass by, so the MinHash is then 1. For checkpoint C, only vehicle 2 and 3 pass by, so the MinHash is 2, and so on. We can then construct the lookup table on the right. A black cell means that with high probability the vehicle visited this checkpoint, since the hash of the vehicle equals to 1 of the checkpoint. White means the vehicle did not pass that checkpoint, otherwise the checkpoint signature would have a lower MinHash value. And gray means that we cannot tell if the vehicle visited the checkpoint or not. From the lookup table, we see that we can recover the full trajectory of vehicle 1, just from the checkpoint signature, and recover part of the trajectory for vehicle 2 and 3, breaking the privacy claims of the system. For our experiment, we took 30,000 trajectories from vehicles in the city of Porto. We define a grid of 88 by 88 representing all checkpoints. Here we see a heat map of all the trajectories. Each cell is a checkpoint, and its brightness is proportional to the number of vehicles that visited. Here we can see the target trajectory on the left and the one recovered by our attack on the right. Recall the colors. Black means the vehicle visited the checkpoint with high probability. White means that the vehicle cannot have visited the checkpoint. And gray is for when we cannot tell. The attack isolated the vehicle behavior to 2 possible trajectories. We also know that 1 is very likely to be part of the vehicle trajectory due to hash values being equal between the vehicle and checkpoint signature. Here we have another example. The trajectory is hidden within others, colored in gray. However, it is still possible to isolate some checkpoints that are very likely to be part of the target trajectory, colored in black. Considering the 30,000 trajectories on average, our attack can reduce the set of possible checkpoints visited by a vehicle to around 10% of the possible checkpoints. Here we have the cumulative distribution function of the size of anonymity set for the checkpoints. The x-axis represents the possible anonymity set sizes on a logarithmic scale. We see that a significant number of checkpoints are never visited, around 60%. 1% of checkpoints have an anonymity set size of 1, highlighted in green on the plot. 5% of the checkpoints have an anonymity set size below 30, highlighted by the green and yellow part. This shows that for a small yet substantial fraction of users, it is relatively easy to compromise the privacy of the visited checkpoint location. To conclude, we studied 2 systems that use locality-sensitive hashing to handle user data privately. The system designer considered LSH to be privacy-preserving. However, we showed how to reconstruct a significant part of the private input for just the hashes. For Google FLoC, we could generate preimages that enable efficient civil attacks. From the hashes, we also reconstructed part of user browsing history using GAN. For MinHash hierarchy, we constructed part of the vehicle trajectories that were intended to be hidden by the MinHash, complete at each checkpoint. We also refuted their differential privacy proof. Our finding shows that LSH hashes leak substantial information about private data. LSH is therefore not a suitable building block for privacy system. It is also important to rigorously evaluate the privacy leakage of novel systems that handle sensitive data. The system designer should hopefully already have performed the privacy leakage analysis. I'll be happy to take any questions.
Okay, thank you very much for your talk. We have a question here in the chat, which is, could FLoC be fixed against your attack by tweaking parameters such as the minimum cohort size?
It could make the attack more difficult to isolate users. It would have to generate more users, but it's fundamentally flawed because they use LSH without having a proper mitigation for the just advertising the outputs of the LSH function to every website is not enough to protect the privacy of the input.